Here we are. So the next talk will be from Tim Kokkeler from the University of Twente, and it will be about SNN junction with mixed superconducting potential. Please, the stage is yours.
So good afternoon, everyone. First of all, thank you for this introduction and the opportunity to talk at this conference. So I recently started PhD at the University of Twente and the Donetsk International Physics Center. However, today I will talk about an SNN junction with mixed superconducting potentials, a project that I did under the supervision of Yukio Tanaka from Nagoya University and Alexander Golubov from the University of Twente. So let me first break down the title. So what I mean with mixed superconducting potentials here is that the superconducting potential of the superconductors we investigate both has an isotropic S-wave component, so it's a singlet component, and an odd parity spin triplet component, the p-wave component. And p-wave component can be of several types. For example, the px wave type, the chiral p-wave type, or the helical p-wave type. In this talk, I will focus on the chiral and helical p-wave type and to investigate the differences if we use one of those two types of p-wave superconductivity. So we're going to investigate these types of superconductors in the so-called SNN junction. That is a normal metal bar that's sandwiched between a superconducting electrode and a normal metal electrode. Of course, in this system, we cannot have supercurrents, only dissipative currents. However, there's still a proximity effect. And this proximity effect we will describe by the Usadel equation, because we assume that this normal metal bar is a dirty normal metal bar. So we assume that the contact between the dirty normal metal bar and the electrodes is very good, so that we have continuity of the Green's function on this side. On the other hand, at the junction between the superconductor and the normal metal bar, we will use the Tanaka-Nassau boundary conditions, a generalization of the Nassau boundary conditions to include also unconventional superconductors. So in principle, the system is 2D. However, we assume that this normal metal bar is either much thinner than superconducting coherence length or much wider than superconducting coherence length, so that the Green's function can be assumed to be uniform across the vertical direction. This means that we can solve effectively a 1D equation in the normal metal. However, we do now need to take into account that from the superconductor, modes can not only enter horizontally, but also at an angle. So two-dimensionality appears really in the boundary condition. So we investigated the density of states, pair amplitude, and the conductance. Here I will focus on the density of states and the conductance. So before we can go to the results, we should think on how to compute these. And for this, it's important to look at the spin. So for the S-wave component, we know if we look at the Hamiltonian, we effectively have two blocks of 2x2 matrices, which have, because they are opposite spin orientations, an opposite pair potential, because the S-wave potential is a singlet potential. If we would now add a p-wave, chiral p-wave or px wave component in which the d vector points in the z direction, we know that this comes down to adding delta p to both of these terms, but these terms here are left unaffected. They are still 0. This means that in those cases, we can still decompose the equations into two sets of 2x2 equations. However, if we look at the helical p-wave case, then we know that the x and dy are both non-zero, and they depend on the angle. So the elements here will become non-zero and different for each angle. So an important question is whether we can still decompose equations in two sets of equations for 2x2 matrices, which are much more convenient to solve than the equation for the 4x4 matrices. So to investigate this, we need to make this a bit more explicit. So having zeros in these positions implies to having this what I will call this Y symmetry. So YHY gives us again the same matrix. So for the full Green's function in the bulk of the S plus helical p-wave case, the symmetry is obviously not satisfied. However, we are only interested in the current predicted by the Tanaka-Nassau boundary conditions. So we're only interested in the angular average current that comes from the modes passing through the interface. And if we look at the d factor, we see that the dx component is even in angle, but the dy component it's odd in angle. Therefore, it's convenient to use the symmetry and to transform actually to a basis of x spins via this matrix. And it turns out that if in this basis you compute the contribution to the current in the Tanaka-Nassau boundary conditions from the mode with angle minus phi is related to the contribution of the mode at an angle phi, exactly via this wave symmetry. But in the overall expression, we're using an angular average over this current. And so we're summing up those contributions, which means that the angular average Green's function, so our boundary condition, does still satisfy the symmetry. This means that even though in the helical p-wave case we have this rather complicated dependence of the d factor, we still can use this 2x2 matrix formalism, which means we can use the theta parameterization, which is in the SNN junction very convenient. So now first I will show the density of states. So on this slide you can see the case for the s+Chiral p-wave case, where on the left the s-wave dominant case is shown and on the right the p-wave dominant case is shown. So you see that if the s-wave component is dominant, we have a dip in the density of states near zero energy, whereas if the p-wave component is dominant, we have a peak. However, you see that the magnitude of this dip and peak really depends on the actual ratio of delta p and delta s. Whereas we know that in the one-dimensional case, this is not the case. The reason can be explained from these two quantities. It appears that the zero energy density of states only depends on these two quantities. For the one-dimensional case, where e to the power of I phi is 1, this boils down to the sign of 1 plus or minus r, which can only assume two sets of values. One is attained if r is smaller than 1, that's s-wave component is dominant, the other if r is larger than 1. So p-wave is dominant. However, for the chiral case, we see that these functions become rather complicated functions of r and phi. So for each r, it will be a different function of phi. And therefore, you see that it actually really depends on the actual ratio of delta p over delta s. It's not robust against the inclusion of the non-dominant components. On the other hand, if we look at the helical p-wave case, we see that we do retain this binary splitting, this robustness of the zero energy peak and dip against the inclusion of the non-dominant components. The reason for this is that now for the quantities delta plus or minus, we should look at the eigenvalues of d dot sigma. But the eigenvalues of d dot sigma are always, in this case, plus or minus 1. Therefore, delta plus and minus will reduce to the same expressions as in the one-dimensional case. And we again obtain just the single value if s-wave is dominant and the other single value if p-wave is dominant. So with this, we can also look at the conductance, the charge conductance case. So the pattern is again similar. We see there are some qualitative similarities, but also some differences. So first of all, we see that if the p-wave component is dominant, we have a zero bias conductance peak, which consists of both a small peak on the order energy and a broader dome-like peak on the order. We see that this feature is actually robust against the inclusion of having also an s-wave component in the pair potential. We still have this two-peak feature, which is good to note. On the other hand, if the s-wave component is dominant, this large zero bias conductance peak is absent. So there are also some differences, like for the zero energy peak and density of states, the zero bias conductance peak is robust against inclusion of an s-wave component for the helical case and not for the chiral case. And if we look for example, for the s-wave dominant case to larger energies, then we see that for the chiral p-wave case, we here have a rather smooth, broad peak, whereas for the helical p-wave case, we see two much sharper peaks around delta s plus or minus delta p. So we see that this charge conductance is also a good tool to distinguish between the s plus chiral p-wave case and the s plus helical p-wave case. So then the last quantity that I wanted to highlight is the spin conductance. So spin conductance may sound a bit strange because in normal superconductors, we do not see them. However, if we look at the pair potential for the s+p-wave superconductor, we see that here there is a spin independent term and a spin dependent term. which indicates that we have some polarization of spins. And indeed, if we, in the calculation of the conductance, we allow the distribution functions for spin up and spin down not to be equal, then we see that in case we have only an S-wave potential or only a P-wave potential, they automatically become zero. But if we have both components, then they become non-zero, and we get a spin conductance, difference in conductance for different spins. So I plotted them here for the chiral and the helical P-wave cases, and with the dotted lines I indicate where delta S plus or minus the magnitude of delta P is. So you see below delta S minus delta P, there's almost no effect, and above delta S plus delta P, it also decays down to zero, but between those two values, it can become rather appreciable, not so small. However, so this is a nice feature to distinguish between the pure S-wave and pure P-wave cases and the mixed potential cases. However, it's not convenient to distinguish between the case of the S plus chiral P-wave and the S plus helical P-wave. Yes, there are some differences, mainly that the helical P-wave case has much sharper features. However, in experiments, most probably sharp features will be smoothed out anyway, and then this one will not give that much of a difference. However, we've come up with another junction, the the corner junction, which is basically two S&N junctions, but then rotated by 90 degrees.
11 minutes.
Okay, yeah. So if we now look at this junction, then we see S plus chiral P-wave case, the D factor always points in the C direction. So if we look at the horizontal bar and the vertical bar, the spin conductance will always concern spins up and down in the C direction. On the other hand, if we look at the S plus helical P-wave case, we saw that if we look at the horizontal junction, we saw the cosine doesn't average to zero, but the sine does. So we transform to a basis of x spins, which means that our current will now be different for spins polarized in the x direction. However, if we now look at the vertical junction, the cosine will disappear, whereas the sine phi will still be present, which means that in this case, actually, we have a current that's polarized in the y direction. The conductance difference for spins in the up and down in the y direction. So this brings an idea of how to distinguish also the S plus chiral P-wave and the S plus helical P-wave case in using the spin conductance. So the conclusion is, well, we saw a sharp distinction between the case where the S-wave is dominant and the case where P-wave is dominant, as expected. And we looked at three different quantities, the S plus chiral P-wave case and the S plus helical P-wave case. So for the local density of states and the charge conductance, we saw that the qualitative patterns are relatively similar for both cases, but there are some clear features that most notably the zero energy behavior, which is robust against the inclusion of a non-dominant component for the S plus helical P-wave case, and not robust against the inclusion of the non-dominant component for the S plus chiral P-wave case. For the spin conductance, well, we saw is if we have mixed pair potential, it disappears for pure potential, so only spin triplet or only spin singlet superconductors. However, we saw that in the S&N junction, we cannot really use it to distinguish S plus chiral P-wave and S plus helical P-wave conductance. For this, we came up with the corner junction, in which we see a clear difference between the S plus chiral and S plus helical P-wave superconductors. So with this, I would like to thank you all for your I look forward to answering the questions.
Okay, Tim, thank you very much for the very nice talk. We have time for one question. Well, then maybe I have one. So do you have in mind any specific experimental implementation of this setup? Because I mean, the signature that you have, especially to distinguish these two cases, is quite interesting. So do you know if someone is working on that, or if there are?
Oh, yeah, I know that these potentials may appear in non-centrosymmetric superconductors, and in many cases, it's not yet quite known which exact pair potential it is. So we hope that can be used by experimenters on those type of junctions. Yes.
Okay.
Thank you very much.
You're welcome.